because that's too difficult. Okay, but here in a second order case, this will not be the case. That if you, let's say, you have a complex root that have, let's say, from lag polynomial, that will have a absolute value which is greater than 1. So it's not necessary here for that. Okay. Now, guys, if this is the case, right? Okay. So then what I'm doing here is I'm going to calculate the product of the two. So you have Z1 times Z2. Okay. So what is going to be? So Z1 times Z2. So multiplying the two roots here. Okay. So I have two roots, Z1 and Z2. Z1 by getting, you know, plus the square root here, and Z2 by getting minus the square root. And if I multiply the two, what do I get? Okay, so let me just write it down. So here you have A1 plus the square root, okay, of A1 squared plus 4 times A2 divided by negative 2 times A2. That's the first one. And you multiply this by A1 minus the square root, okay, of A1 squared plus 4 times A2, all right, okay, divided by negative 2 times A2, okay. So the question is what you get if you multiply the two roots, okay. Now if you multiply the two roots, then basically in the denominator you have 4 times A2 squared, that's obvious, okay. And here you apply the formula, so here you have, let's say, x plus y times x minus y equals x squared minus y squared. So here you have A1 squared minus the square of the root. Okay, and the square of the root is basically what you find underneath. So here you have minus A1 squared plus 4 times A2 squared, 4 times A2. That's going to be it. Okay? Now here you have, obviously you have A1 squared minus A1 squared, which is 0, and you have plus 4, 8 times 2 divided, so negative 4 times 8 times 2 divided by 4 times A2 squared will be equal to negative 1 over A2, guys. Okay, so if you multiply the two, then you get negative 1 over A2 as a result. Okay, so if you multiply the two roots by each other, then you get negative 1 over A2 as a result. Now, guys, if, let's say, the absolute value of the first one is greater than 1, because that's necessary for the process to be stationary, guys. Okay, so if the process is stationary, then the absolute value of the first root is greater than 1. And, okay, so then the absolute value of the second root is also greater than 1. Okay? So if that's the case, right? And why is that? Because the process is stationary, obviously. Okay? Then this implies, obviously, that the absolute value of the product, okay, of the two is also greater than 1. Again, so if the absolute value of the first one is greater than 1 and the absolute value of the second one is also greater than 1, then this implies that the absolute value of the product of the two must be also greater than 1. Of course, and this is not true the other way around. Okay? Now, of course, if the product of the two is equal to negative 1 over A2, then this is going to be equivalent to the fact that you have the absolute value of negative 1 over A2, which must be greater than 1. Right? So the absolute value of negative 1 over A2 must be also greater than 1. Why? Because the product of the absolute value of the product is also greater than 1. Okay? Do you get that? Okay? Now, of course, here you have, yes, you got a question?
Yes, we have in 1 that the absolute value of A2 is smaller than 1, so one can
yes.
just conclude that 1 over A2 is larger than 1?
Yes, so then here you have basically, that's what I'm going to come into. So this is the absolute value of 1 over A2, right? So the absolute value of A2 is just larger than 1, which is equivalent to that the absolute value of A2 is less than 1. Okay, so
is that we want to prove?
Yes.
Oh, it's not.
Yeah.
It's
that's going to be it. So that's finally, that was the first condition, right? So that was the first condition here of the stationarity triangle, basically. So that was the first one, right? So that's where it's coming from. Okay. So if the absolute value of this coefficient is not less than 1, then the process cannot be stationary. Okay, so you will automatically recognize if it's not stationary by, you know, I mean, let's say if this coefficient or the absolute value of this coefficient is not less than 1, then it cannot be stationary. Now, depending on what you have for the others is something else. Okay, so for the others is a different story. But the first, okay, so but the first first coefficient A2 has to have an absolute value which is less than 1 for the process to be stationary. Okay, so again, this is just a necessary condition, not a sufficient condition for stationarity, right? You get a sufficient condition by the other two, okay, but which I'm not going to prove here, but that's basically what you're going to get. All right? Does it make sense? Okay. So if you say a process like, for instance, whatever, let's say you have whatever yt equals, let's say 1 plus 0.1 times yt minus 1, okay, minus 2 times yt minus 2 plus the white noise, then what can you say? Basically you can say that process is not stationary, period. Okay, because the absolute value of the coefficient A2, okay, which is of course A2 is equal to -2, right? It's greater than 1, or greater or equal to 1. Okay, so it has to be strictly less than 1. Okay, so this process is not stationary. All right, you can see that immediately, obviously. Good. All right, guys. Okay, so this is just, you know, a simple example for that. Okay, so this process is not stationary. Okay. Now there are of course multiple ways to show that. Okay, when is the process? I mean, let's say you get a second order autoregressive process, and in the exam, and you're supposed to show that the process is stationary. What do? You have two options. Okay, the first option is you show that the roots, okay, of the polynomial have a absolute value which are all greater than 1. Okay, that's the first thing you can do. And the second thing you can do is, okay, you can check whether or not the points are in this stationary triangle. Okay, so you have two options basically to show this. Okay, it's up to you. So let's say I'm giving you a process, you have to show that this is stationary. You have two options. First, you calculate the roots of the Lac polynomial and examine whether or not the absolute values are greater than 1. If they are, then the process is stationary, period. Okay? And the second option that you have is you look into this you set up the conditions here for the stationary triangle and see whether or not all conditions, all of them, all three, are jointly satisfied. If that's the case, then the process is also stationary, period. Okay? You understand this? That could be a typical example for your exam. It's not difficult, I think. Okay? Right? But you have to remember these. Okay? Good. All right, guys. Any questions related to this? No, right? Or is this clear? Okay? Good. And for high order, I mean, if you want to have a different representation, then you would have a high order. For high order, you're supposed to calculate the Taylor polynomials, but I'm not going to do this in the exam. Okay, so for the exam, it's not going to be relevant. Okay, so you don't need to apply the Taylor series here involving that. Okay. Could have done this, but I'm not going to do it. Okay. It's basically more interesting for high order processes. I did this for the first order one, but you could do this for high order processes as well. Okay, and for second order, it's also not that important because you have the stationary triangle and you have also the roots of the Lac polynomial, which results in a quadratic equation. All right, guys. Now, okay, so let's solve one or two exercises. Okay, finally. So basically, what you have, that was it for chapter 3.1. Okay, so in this case, exercise 3.1, exercise 3.1 is already done. So I did this. Okay, so the process is stationary. I've proven that. Okay, we did this, so we can skip that during the lecture. And exercise 3.2 is just for you to practice. It's going to be the same thing, but in exercise 3.2, you have that basically that the time is not bounded from below. Okay, so if the time is not bounded from below, okay, then you would have a different representation. So if in that different representation you have asymptotically stationarity. Okay, so the process is just asymptotically stationary, but not stationary in general. Okay, that's what you have. Okay, exercise 3.3 was about the Taylor polynomial. Okay, so this is something that you don't need to consider. Now there are parts of the exercise 3.4 which we didn't consider. Okay, so exercise 3.4. Okay, so first off, you have a process. Okay, so the process is you have a constant plus 0.3 times yt minus 1 plus 0.1 times yt minus 2 plus the noise. Okay, so basically you write this in terms of the lag polynomial. You have the first coefficient is equal to 0.3 and the second coefficient is equal to 0.1. Okay, now if you want to examine whether or not this process is stationary, again you could do the following. You could set up the lag polynomial, calculate its roots, and see whether or not the absolute values of the lag polynomial, of the roots of the lag polynomial are greater than 0, all of them. This is what we have done. Okay, so I'm not going to do this again. This is what we have done. Maybe remember that the first root was, I think, 1.25, and the second root was equal to -2. Okay, so let me just summarize that. So the lag polynomial is equal to 1 minus 0.3 times z here, if you use an argument z, minus 0.4 times z squared. And if you calculate the roots, okay, so then you would find z1 is equal to -1.25, and z2 was equal to -2. Okay, so this is 1 here. Okay, 1.25 and -2. So the roots have an absolute value which are greater than 1. Hence, the process is stationary. We did this last time. I'm not going to repeat that. Okay. Now the second option that you have, and this is also considered in the example, okay, is that the coefficients, or the pair of the coefficients, is in the stationarity triangle, right? And that involves looking at the conditions. Okay, so the first condition was that the absolute value of A2 is supposed to be less than 1. Okay, so the absolute value of that is going to be, of course, equal to absolute value of 0.1, which is of course 0.1, and this is less than 1. So the first condition is satisfied. Okay, so the second condition is about, you know, having that 1 plus A1 minus A2 is greater than 0. Now this is also true because you have 1 plus 0.3, obviously, minus 0.1, and this is going to be equal to 1.1. Okay, so which is of course greater than 0. Okay, so the only thing that matters is just greater than 0. And the third condition involves that 1 minus A1 minus A2 is also greater than 0. So here you have 1 minus 0.3 minus 0.1, which is of course 0.6. So this is also greater than 0. So that also, this condition is also satisfied. The coefficients are in the stationarity triangle. That's quite obvious, right? So then the process is also stationary, right? So you can choose whether or not you wanna apply the first or the second rule. It doesn't matter. Okay. So the process is stationary. That's what we conclude. Okay, in both cases. Good. Any questions? Okay. Now, if an autoregressive process is stationary, okay, and we're coming back to that. Okay, so this is what we also considered. So, if let's say an autoregressive process is stationary, okay, it is possible. Then it is possible to represent the process as follows. So here you have the constant, over the lag polynomial at point 1, okay, and then plus, okay, so then you have, okay, these coefficients alphas, okay, so these alphas that are not specified in general, okay. I mean, they exist, but it depends on the process itself, so it's no longer specified. But you have these noises here. Okay, so epsilon t minus j. There is a possibility for that. Now, using this expression, but you can basically calculate what the expectation of the process is. Okay. Now, if you take the expectation of the process, and that's quite easy. Okay, so this is basically part of the exercise 3.5, I think, or 3.7. Or 6, whatever. No, it's the last one where you have the linear processes. It's relatively easy to calculate the expectation here of the process. So the expectation of the process is going to be the expectation of the whole thing, right? And here you have the expectation of a linear transformation, which is the linear transformation of the expectation. So here you have the constant, okay, plus the expectation of the sum. Now, guys, the expectation of the sum is equal to the sum of the expectations, right? Expectation of the sum is equal to the sum of the expectations. So here you have the sum, okay, of the expectations of these linear transformations here. Okay, so you have alpha j times epsilon t minus j. Okay. All right. And the expectation of a linear transformation is, of course, equal to the linear transformation of the expectation. So here you have the constant, okay, plus the sum of these expectations. So here you have basically that this is going to be equal to alpha times the expectation, okay, of these noises. And the expectation of these noises are what? All of them are 0 at all times, right? So the expectation of the noises are 0. So then basically the sum is going to be equal to 0. So the expectation of an autoregressive process is going to be always equal to the constant over 1 over the lag polynomial at point 1. That's the expectation of the process. That's how you would calculate it. And that's relatively easy. Okay? So for instance, I mean, let's just give you an example, okay, which relates to the following proposition. So let's say, for instance, if you have yt equals, let's say, 2, what do we have here? 2 plus 0.3 times yt minus 1 plus 0.1 times yt minus 2 plus epsilon t, okay? So then, of course, the process is stationary, okay? We have already seen this, okay? Because the roots, blah, 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 and so forth, okay? We do not need to consider. Now, if the process is stationary, what's going to be the expectation, okay? What's going to be the lag polynomial? And I mean, of course, the lag polynomial is going to be equal to 1 minus 0.3 times L minus 0.4 times L squared, okay? So if you calculate the lag polynomial at point 1, you get what? So you get 1 minus 0.3 times 1 minus 0.4 times 1 squared, which is going to be also equal to 1. So we have 1 minus 0.3 minus 0.4 equals 0.3. That's going to be the lag polynomial. So basically, I mean, you have this, that the expectation of the process, all right? So then the expectation of the process, as you can see this here, it's going to be equal to the constant. The constant is 2 here. So the 2 divided by the lag polynomial at point 0.3, okay? So basically 2 times, okay, so 2 divided by 0.3, and what is 2 divided by 0.3? This is going to be 2 divided by 3 over 10, so this is 2 times 3 over 10 over 3, which is going to be equal to 20 divided by 3. That's the expectation of the process, okay? So that's how you would calculate the expectation. Right? Okay, according to this formula.
The coefficient of yt minus 2 is 0.1 or 0.4? It's like
I don't understand.
the coefficient, the a2.
The v here, this one. This is 2 here.
Yeah, and a2 is 0.1, right? a2?
A2?
That goes with yt minus 2.
I made a mistake. Yeah, sorry guys. Yeah, 1. Oh yeah, I made a mistake. I didn't see this. Yes, sorry. Instead of 0.4, I have it 0.1. Yeah. I'm getting tired now. It's too late for me, right? Okay. Good. Okay, so 1 minus 0.3 minus 0.1 is going to be equal to 0.6, right? Obviously. And then you would have that the expectation is equal to 2 divided by 0.6, okay? Right? So this is just going to be 10 over 3, right? Okay? So, apologize for that, okay? Now the variance is not that easy because the variance is depending on basically on these coefficients alpha 1 and alpha 2 and so forth, and it's not quite clear what it is. But basically, I mean, you could do this. Okay, so we did this for the autoregressive process where the order was equal to 1, so the first order autoregressive processes. But we should look at the variance. At least we should check that the variance is not depending on time, right? Okay, so the variance does not depend on time. So what you can do by just basically calculating it, okay, so the variance, okay, of the process is going to be equal to the variance, and we have it here, so the variance of v over a of 1, okay, so that's a representation of the Lac polynomial, and then plus, and here you have these coefficients, okay, so j is equal to 0, here you have plus infinity, and then you have alpha j times epsilon t minus j. Okay? Now, of course, the variance does not depend on this additive constant here. Okay, so this is going to be the variance of the sum, and the variance of the sum is equal to the sum of the variances, right? So, I mean, the white noise is independent. Okay, here in this case, and not just independent but uncorrelated. But here, uncorrelatedness is enough. Okay, so here you have the sum. The variance of the sum is going to be equal to the sum of the variances. Okay, so here you have the variance of the linear transformation. Okay, so alpha j times the white noise. Okay. And the variance of a linear transformation is going to be, okay, so here the constant times the random variable is going to be equal to the square of the constant times the variance of the random variable. Okay, so here if you want to get rid of this coefficient here, then basically what you do is, okay, so basically what you do is you have alpha j squared times the variance of the white noise, okay? And the variance of the white noise, we denote this by sigma squared, okay? So the variance of the white noise was sigma squared. Okay, so this is going to be sigma squared times the sum, okay, of these squared coefficients, guys. Okay, so the square of these coefficients. Okay, now this thing here, okay, so this thing is finite because the coefficients are absolutely summable. So if the coefficients are absolutely summable, then they are quadratically also summable. This is an implication that we can basically have. Okay, so that's all. But that's all you know about them. Okay, so in general you have to specify the coefficients first, and then you have to calculate the corresponding sum, and this is going to be equal to the variance of the process. Okay, now you can do this. Okay, for the covariance, I'm not going to do this here. I'm going to skip that. But it's an exercise, okay, so you can calculate the covariance, okay, so the covariance of the process, okay, if, let's say, the process is stationary, and you could do this as an exercise. That's, I'm going to leave it to you. We already did this in exercise 3.1. It was quite similar. The only exception was that we had different coefficients. That was it. Okay, so basically this is what we have, and the result will be, okay, so I'm going to tell you the results so you can check it out for yourself. Okay, so this is going to be sigma squared times the sum, okay, Okay, so this infinite sum. So here you have the coefficients. Sorry, the coefficients alpha j times alpha j plus h. Okay, so the covariance with respect to this leg here. Okay. Okay, so that will be the result. You can do this as an exercise if you like. Okay. All right. Now, of course, it's not practical to do it like this. Okay. So, more practical would be by applying the U-Walker equations. Okay. So if you apply the U-Walker equation, then basically it's easier. Okay. So, but I'm not going to do this. Okay. So because I think I'm going to stop the lecture here. I need more than 5 minutes for that. So since I need more than 5 minutes, I don't want to interrupt that. So I will start, proving the U-Walker equations tomorrow. U-Walker equation tomorrow, and then we will check out how to calculate correlations from the practical perspective, which are better in this sense. Okay, so I'm not going to do this now. We're gonna skip that, and I will do this next time. Okay. So for the next time, and because I need more than 5 minutes to prove the U-Walker equation. Okay, so then we prove the U-Walker equation, then we apply. Okay, so I'm going to stop here, and yes, I will evaluate your assignments too. So I will upload the solutions to the assignments, and basically and evaluate yours. But I think it looked good, so I think almost everybody has it correct. Okay. So it was fine, not a problem. But I would be very, very happy if you try to send me the things in a way that it's printable, so I can give it back to you. I mean, I already complain about this. Okay, so at least I hope that you don't write your seminar paper, or let's say it's not going to be handwritten, right? Okay, so if it was in the 1970s, okay, I would understand that, but in the year 2018, it's quite probably, it's a different thing, okay? So, I mean, you are more sophisticated in this than I am, okay? So you know probably more about these mobile applications than I do, so basically, I think it's not over-exaggerating if I say that it's not intellectually challenging for you, okay, to submit this by electronic editor, okay? But it's up to you. So if you want to submit assignments using handwritten notes, then it would be better if you just give it to me in the lecture, okay? So then I can correct this and give it back to you, so provide you with some feedback, okay? Because I'm not going to waste my printer on printing your gray and black backgrounds, okay? All right, guys, I apologize for that. Okay, now, if you don't have questions, then we see each other tomorrow, okay? Thanks a lot.